Okay, welcome to the second lesson on impulse. It's really just a little quick finish off, not much to go through in this. We're just going to look quickly at how does impulse link in with impacts and collisions. You'll probably do more in lesson in terms of practical on this, and then just really talk very, very briefly about car safety and the parts of the design of a car that use this idea of impulse in their actual design. Okay, a little bit more on impulse, just to finish off from the last session. We defined impulse as the time that a force acts for. So force times time is our definition of impulse here. It's delta mv. Just I want you to think about the three ways that we could change the impulse. These are the three possible ways we could apply. I suppose your average way of doing it is a medium force over a medium time. So your F delta T, both the force and the time are sort of just averaged out or whatever. They're not neither one is, force isn't massive and the time isn't particularly short or long. So here I've shown this by just the size of the font that I'm using. What you could do though, you could apply a large force over a very small time. So here I've got a really big F with a small delta T, and this would give me the same impulse as in the first example. The third way I could do it, I could apply a very, very small force, so a little f, and I could apply that over a long time period. And this would also give me the same impulse. This changing of the force and the time is key to your understanding of what goes on in collisions and impacts. We're going to look at just a couple of thought experiments. Apply the above to explain why it is much better to stop yourself running by hitting a haystack rather than a brick wall, and using a bungee cord that stretches rather than a rope that doesn't particularly stretch to throw yourself off a bridge. And if you stop and think about both of these examples, you want to be using the final thing here to describe them. So you're using a smaller force over a longer time in both of those examples. Okay, let's just put some numbers on this. If we imagine a rebound impact, you do sometimes get questions on considering the change in momentum if a ball hits a wall and bounces back at the same speed. So if we look at this example, we've got this ball hitting the wall and then bouncing back. Its momentum on the way in we've described as minus mv, and its momentum as it's rebounded is plus mv. Why do we do that? Well, you're well used to vectors by now. We've said going from right to left as being negative and from going left to right as being positive. That's fairly standard. We normally say that going this way is positive and going this way is negative. So if we just think about the change in momentum, we define the change in momentum as the final momentum minus the initial momentum. That will give us the change. So if we say the final momentum is this value plus mv, and then the initial momentum is this value minus mv. So the change in momentum is the plus mv, which is the final momentum, minus the initial momentum, which is minus mv. These two minuses together give us a plus, so the final overall change in momentum is plus 2 mv. So this is sort of saying that if you are in a car that bounces off something, if you undergo that impact, then your change in momentum, you haven't just stopped by hitting the wall, you've actually hit the wall and bounced back at the same speed you were going at. So your change in momentum is actually twice. So that could inflict quite large injuries if cars just bounced off each other. This is why that we don't just fit rubber bumpers on cars, so that when they hit things they just bounce off in the opposite direction. If you were in a car that did that, you would find yourselves having quite serious injuries. If you've ever been on bumper cars at fairgrounds, you'll probably know what I'm talking about. If we look at force, exactly the same treatment here really. Right to left is negative, left to right is positive, but this time we're going to use the force, and force is delta mv over delta t. So if we just shove that into our thinking with the momentum before is minus mv, the momentum afterwards is plus mv. So here our change in momentum is still the same, it's plus 2 mv, but to get the force we divide it by the time of the impact. So we can see our overall force is in the positive direction, which is away from the wall, which sort of, I always think it sounds quite sensible. If you were that ball hitting the wall, you would feel as though the wall has pushed you away in the positive direction. So that's sort of that's the equation proof of the direction of that force. But remember, it's twice what you might think it would be because you're stopping and then going back in the same direction that you came. I'm not going to talk for longer than a minute about this, but crumple zones in cars are built purely to increase the time that it takes for the car to stop. Side impact bars strengthen the car in collisions from the side, but the reason a car crumples up is so that you stop, or the car stops with you in it. The car stops over a longer period of time, therefore reducing the force on the occupants and the car, hopefully. Seat belts, they hold you in place, obviously, but what they actually do, they stretch a little bit, and where they connect to the car body, it peels away. You might have seen this in previous lessons. So again, a seat belt stops you over a longer period, so it reduces the force on you. And it also avoids you having a second impact, and a second impact is if you hit the dashboard. So there's something else in a car as well that will help you, an airbag in most cars now. Just like the crumple zones, really, they increase the amount of time over which the force has to act to change a car driver's momentum. If you're sitting in the driving seat, you have got to lose your momentum. If you're travelling at 30 miles an hour and the car stops, you've got to stop as well. So you need to stop, you need to lose your momentum, but to reduce the force on you, you need to do this over the longest time possible. And that's exactly what an airbag does. It stops you hitting the dashboard. And if you hit the dashboard, you'll probably stop very quickly. So you'll have a small time and a massive force.